Hello everyone, today's Mark speaker is Kyle Salois, hailing from Denver, Colorado. And he will be telling us about merging chromatic symmetric functions and Hessenberg varieties. Hi everyone, I'm Kyle. Thanks for that lovely introduction. I'm going to be talking about chromatic symmetric functions and Hessenberg varieties. If you were here back in the spring, this is going to be roughly the talk that I gave that time, but pushed about 50% further, because I know about 50% more than last time. Probably a lot more than 50%, but I only fit so much in an hour. Okay, so the object of interest today are going to be Hessenberg varieties and chromatic symmetric functions that are sort of associated with them. In order to talk about those, we have to start with something called a Hessenberg vector, sometimes called a Hessenberg function. Today we'll call it a vector, which is going to be h, which is h of 1 through h of n, satisfying two properties. So first of all, we need that the sequence is weakly increasing. So h of I is less than or equal to h of I plus 1. And we need that h of I has to be at least I. So best viewed by example. There's 3 examples of Hessenberg vectors. We might have something sort of on one end of trivialness, where I had to have 1, 2, 3, 4 through n. So I'm sort of on the lower bound of this and strictly increasing. I might be on the other side of trivialness, where my vector is just all n's. Right, so then I'm sort of adhering to the lower bound there, but I'm as high as possible. And we could have something somewhere in the middle, somewhere along the lines of maybe like 2, 4, 4, 4. It's going to be a bit of a running example for us today. So these are, there's a combinatorial bijection between these and dict paths, where the entry hi tells you the height of the ith sort of step of your path. So a dict path is a path from 0, 0 to n that stays weakly above the diagonal. So our first path might look like that. Our second path is going to go all the way up, all the way over. And you can kind of see how any Hessenberg functor is going to make a function or vector. I can't combine those words. That's a different word. Any Hessenberg vector is going to give us some path that stays above the diagonal. And
do they have to be integers or?
yes, they do have to be integers. Thank you. So let's say that this lives inside of n to the n.
You could say z to the n, because then your other condition was. Oh no, I guess there's has to be.
Well, so the entries are all going to be from 1 through n.
Yeah.
So we'll just call it that. Okay, we're going to start with the chromatic symmetric function side of things. We're going to do that by building up a graph. So the chromatic symmetric function, the word chromatic comes from the chromatic number of a graph. And so we're going to start building up a graph from a vector. So the unit interval graph GH associated with a Hessenberg vector H is going to, it's a graph, so there's vertices and edges. The vertex set is again just the natural numbers from 1 through n. And we're going to have an edge from the number I to the number j if h of I is at least j. So h of I tells you which edges the vertex I connects to. So a couple of examples. For my sort of lowest Hessenberg vector, this tells me vertex 1 cannot connect to anything above 1, vertex 2 cannot connect to anything above 2. This is just a graph of 4 isolated vertices, and we'll label them 2, 3, 4. For the other extreme end, if I have like 4, 4, 4, 4, that tells me vertex 1 is connected to everything from 1 to 4, vertex 2 is connected to everything from 2 to 4, and so on. So 1 goes to 2, 1 goes to 3, 1 goes to 4, 2 goes to 3, 2 goes to 4, and 3 goes to 4. And finally, our slightly more interesting example, 5, 2, 4, 4, 4. This tells me vertex 1 only goes to vertex 2, vertex 2 goes to 3 and 4, and vertex 3 goes to vertex 4. These are called unit interval graphs because they can be realized as an intersection graph of unit intervals in the plane. So this would be like 4 disjoint intervals of length 1, 4 intervals that all overlap each other, and some intervals with some overlap and some not overlap.
So if you had like 2, 3, 4, and n, like 2, 3, 4, dot, dot, dot of the n, that's
Yeah.
just the path of the graph, right?
Yes, that would be a path graph. That's a good example.
I mean, you don't add it, but, no, 2
Thank
insertion
you.
trees,
Yes,
yeah.
yes, yes. 2, 3, and give you a path. Because 1 goes to 2, 2 goes to 3, and so on. And also, for the sake of something we do later, we're going to direct all of our edges sort of in the direction you would expect from the lower labeled node to the higher labeled node. Okay. Next, a proper coloring of a graph. So, a proper coloring, kappa of a graph G is a function kappa from the vertices to the natural numbers. You want to think of this as your set of colors for the graph, such that if ij is an edge, then the coloring sends the vertices to different colors. So the color associated with I is different from the color associated with j. So let's just draw a couple examples of proper colorings, maybe on this graph right here. And it's fun to use colors, so let's actually color them in. All right, so if I color this first vertex red, then this vertex has to be colored differently because I have an edge here. So maybe let's go with green. This vertex right here can't be green, but it could be red. So maybe let's make it red. And finally, this vertex is touching a red vertex and a green vertex. So it has to be a third color entirely. So we'll go with blue. And we're going to label our colors by numbers, again, because our set of colors is the natural numbers. I'll pull a Henry Adams and make these on board. So that's one proper coloring. Right? You can imagine that there's a bunch of these. And from the colorings, we're going to build up a symmetric function. So, the chromatic symmetric function which we're going to denote x subscript g, is the sum over proper colorings of the graph G. And I'm going to assume that the vertices are labeled 1 through n, so this is just going to be a finite graph. And so we're going to have x kappa 1, x kappa 2, all the way through x kappa n. So you're just taking the product of x with the index corresponding to the color assigned to each vertex. So the monomial for this coloring, so one of the summands of that sum is going to be x1 squared, these have 2 vertices colored 1, times x2 times x3. And we're summing up over all possible proper colorings of this graph. Why is this a symmetric function? Well, for every coloring I have of the graph, I can switch 2 colors, and that doesn't make it an improper coloring anymore. Because, if I was touching something bad before, I'm still touching something bad. So maybe let's switch 2 and 3. That's not useful. Let's switch 1 and 2. So here's a coloring where I have 2 copies of the color 2, 1 copy of 1, and 1 copy of 3. So I get the monomial x1, x2 squared, x3. And this works for any permutation of your colors. And so if I have this monomial somewhere in my sum, I also have every monomial where I swap the indices. And I could even do colors like 4, 7, and 20, right? Because I'm just going to the natural numbers. Okay. So for this graph in particular, we can count all the colorings. There are, I believe, 28 proper colorings of this graph. So X, G.
With the maximum number
Oh, yeah,
of colors?
yeah. So up to
four
a
colors?
Yeah.
Yeah.
So
Because you have up to n there, for, you know.
yes. So technically, this symmetric function is infinitely many terms.
Right.
But we're going to group them all up by the terms corresponding to certain, I guess, minimal colorings by order.
You can just say where the exponent vector is a partition.
Yeah.
Right. And those are the leading monomials that you'll get, and then there's 28 leading monomials.
Yeah, so we're going to express this in the monomial basis.
Although not 28.
There's 4 and 24 in here. So I believe we get 24.
Like two types.
Yes, 2 types of colorings. Yeah.
Oh, I see.
Okay, so these m's are the monomial basis of the algebra of symmetric functions. But how you should think about it is m1111 is counting the number of colorings with 4 different colors. And 4m2211 is telling you that there are 4 colors where I have 2 of the same color and then 1 each of 2 different colors. So this could be color 1, 2, 3, 4 and 1, 2, 3. Right, you're always going to get n factorial copies of this one, because if I'm using all 4 different colors, I can just put them on vertices however I want, and there's n factorial.
Sorry, why did you get 12? Because you're only using 3 colors, but
So I'm on.
so you have the double can be 4 colors, but then the other ones have 3 choices.
So this, yes, so the colorings where I have 2 1s, a 2, and a 3, and the colorings where I have 2 2s, a 1, and a 3 are both included in this, because this monomial includes things of the form x1 squared, x2, x3, and x1, x2 squared, x3, and so on.
Right, but the point is for that one, for instance, you have to actually sort of move where the 1 is to get the coefficient of 4. So like those other terms are just from like switching the role of red and green.
Yes.
Right? But like I think what you want is also to say like 1, 2, 3, 1 is like another way of ordering 2 1s and 1, 2, and 1, 3, so that you get the coefficient of that leading monomial, x1 squared, x2, x3.
Yeah, so let's just write down all the colors of this graph, just so we're all on the same page.
Yeah.
So I'm claiming there's 4 of them. So I need 2 copies of 1. Let's do 2 red vertices. I need 1 blue vertex and 1 green vertex. Sorry to the camera if you can't see this.
You probably rotate it a little
Like that.
You're good. Don't worry about the camera. Do your thing. Yeah.
Okay. So let's start by figuring out where our 2 red vertices are. Well, if I put a red vertex here, this can't be red, but this could be, or this could be. And actually, I have 2 colorings for each of those, because I can swap where the blue and the greens go. So if I go red, blue, or red like that, hidden the green from myself. Green could go over here, green could go here, and like this. I believe those are the 4 proper colorings with this set of colors. And that is why we get a coefficient of 4 here, because that's corresponding to 4 of these monomial terms. Right, if I swapped the roles of color 1 and 2, I would get these 4 terms, but these are both included in the monomial symmetric function. Okay.
Your variables are x1 through x4.
In this case, we're going to think about these as symmetric functions, so formal power series. So in fact, your variables are x1, x2, x3 all the way. Your But you can truncate it at any, as long as you truncate at xn at least as large as the number of vertices of your graph, you'll get all the information. You won't lose any. So if you'd rather think about it as like an actual polynomial, you could. And that's what I do all the time, because infinite things are hard.
And just to clarify, the 24 comes from, are you gonna do that next or?
Oh, no, so the 24 comes from,
Yeah, I see that.
yeah, right, I
Okay, just
could,
as Chris asked, so, yeah.
you know, there's 4 different ways of choosing the color there, 3 different ways, 2 different ways, 1 different way, right? Okay, so folks were studying these chromatic symmetric functions, and there's a conjecture by Stanley and Stembridge. Which says that when G is a unit interval graph, this symmetric function is E positive. So E, the elementary symmetric functions are another basis of the ring for algebraic symmetric functions. And saying that a symmetric function is E positive means that when you expand this function using this basis, you have positive coefficients in the basis expansion. We're not super going to go into what E is, but this is a big outstanding conjecture in the realm of chromatic symmetric functions, and people really want to solve it. I think this, I don't think I wrote down the date. It's from like the 70s, I want to say. So it's been open for a while.
Which basis?
The elementary
Okay.
basis. So EK is the sum of I1 not equal to I2 not equal to IK, xi1, xi2. Basically square 3 binomials. Because all my indices are different. Not a lot of progress was made on this front. I mean, they proved this for certain subfamilies of unit interval graphs, but more progress was made by expanding the definition of a chromatic symmetric function into what we're going to call a chromatic quasi-symmetric function. In order to do that, we need to define an ascent. So given a directed graph, a G, and a coloring, proper coloring, but you could actually do it for any coloring if it wasn't proper. The ascent number.
Can I ask a quick question?
Yes.
So this is conjectures for the infinite one, right? And you still, I assume you still have the formula that a basis for all the elementary, for all the symmetric polynomials can be written in the monomials of the elementary. And this is saying that if you express that in terms of that monomial basis, all the coefficients are positive.
Yes. I'm going to answer a question that's hopefully your question, but if it's not, then just tell me it's not. So the elementary symmetric functions form a basis insofar as the algebra of symmetric functions is a graded algebra. It's graded by degree. And the set of E lambda, where lambda is a partition of n, is a basis of the degree n part. So the degree n symmetric functions, I guess. And so when we have some generic symmetric function, this is homogeneous because all of your colorings have n choices of colors. So it's homogeneous of degree n, and so I can express it in terms of E lambda, where lambda is a partition of n. And so these are the basis elements that you want positive coefficients on. Okay, so given a directed graph G and a coloring kappa, we're going to say the ascent number, which is ASC of kappa, is the number of times that you have a vertex or a directed arrow, directed edge from I to j, and the coloring agrees with that order. So in our graph, all of our edges are ordered from left to right. So So all of our directions are pointing from the smaller I to the bigger j. And so this is just when does the coloring agree with that, right? And so in our coloring over here, we had color 1, color 2, color 1, color 3. And so this coloring right here is going to have ascent number. We do get an ascent for this edge. We don't get one for this edge because I'm going down in color. We get one here, and we get one for the over one. And so this has ascent number equal to 3. Hopefully I did another example where the number is different. So this is color 1, color 2, color 3, color 1. This should be different. So I do have an ascent from 1 to 2. I do have one from 2 to 3, but I don't get one from 2 to 1, and I don't get one from 3 to 1. So this guy has ascent equal to 2. So this is some statistic on colorings, proper colorings of a directed graph, which means we can kind of make like a Q analog of a symmetric function. So the chromatic quasi-symmetric function xg of x's and q is, again, the sum over proper colorings. Again, list off your colors as the indices of your variables. But now we're going to multiply this by q to the ascent number of that specific coloring. So this is a Q analog because when you set Q equal to 1, you get back to your original mathematical object, the chromatic symmetric function. But now I have coefficients on these x terms that look like polynomials in Q. And so as an example, let's squeeze that down here. For the graph we've been considering, xg 2, 4, 4, 4. We can expand these as 1 plus 6q plus 10q squared, 6q cubed plus q to the 4th, and 1, 1, 1, 1, and 1 plus 2q plus 1q squared, m2, 1, 1, 1. And so what this is telling us is of the colorings that have 4 different colors, there's 1 that has no ascents, 6 that have 1 ascent, 10 that have 2 ascents, and so on. And for the colorings with 2 of the first color, no, this is 2 of the first color, 1 of the second, and 1 of the third, there's 1 coloring with no ascents. Oh, shoot. Is that right? Oh, yeah, these are all off by a power. There's 1 coloring with 1 ascent, 2 colorings with 2 ascents, and 1 coloring with 3 ascents. And so we can show that over here. So this is color 1, color 3, color 1, color 2. So yes, no, yes, no. This is another one with 2 ascents. And here, color 1, color 3, color 2, color 1, yes, no, no, no. So this guy has ascent 1. And so those are the powers. We pop on the Q's, and we have 2 with ascent 2, so that gives out that coefficient. So in general, this function is not necessarily going to be symmetric, which is why it's called the quasi-symmetric function. However, when G is a unit interval graph, it is a symmetric function.
Can I just interrupt real quick with a comment?
Yep.
Maybe you already said, but I missed it. But for the people in my class, the 1 plus 6q plus 10q squared, that thing, that's the 4q factorial, right? The q analog of 4 factorial. Because I think ascents turn into in that case. Because it's just like
Yeah.
a path, and you're just looking at. Oh, no, I'm wrong. Okay, never mind. Forget that. It's not the same. It's a different Q analog of 4 factorial, which is cool. It would have been if it was the complete graph, but it's not yet.
Since we
So
stopped your momentum,
yeah.
can I ask, is it obvious that there is a symmetry between the the complementary degree of the Q thing?
Not obvious. It would take me about 10 minutes to tell you the proof, but I'm going to spend those 10 minutes doing something else.
Fair enough. But it's true.
But it's true. Yeah. And that's what this theorem is going to be. So, theorem, when G is a unit interval graph, xg, xq, the chromatic quasi-symmetric function is in fact a symmetric function. So the reason that it might not always be symmetric is you might have a different term on, say, x2 or x1 squared, x2, x3, and x1, x2, x3 squared. You might get different coefficients in your q's because if you're not on a unit interval graph, swapping two colors will change the number of ascents you have. But there's a bijection between these and themselves that preserves the statistic. Yeah.
So just to be clear, so you get only unit intervals and you stack them up in some way and they represent the vertices and you connect them if they overlap.
Yeah, so that's why they're called unit interval graphs, but we don't actually need any of that mechanics to talk about these. But that's what the name is from. Okay, and so the Stanley Stembridge conjecture redone. So this is now due to Shareshian and Wachs. A lot more recently, this is past 15 years, I think. XG.
No, a theorem, right?
This is not a theorem, this is the big conjecture.
Shareshian and Wachs.
Shareshian and Wachs defined the chromatic quasi-symmetric function and rephrased the original conjecture in this language.
Oh, yeah, no. I was thinking of the other one. What's the one with,
Garcia Pacheco.
no,
Or, no, that's not.
the one that was proven with the cohomology ring.
Yeah. That's common. Brosnan and Chow.
No, that's who proved it.
Oh,
It was Wachs and somebody else. I think it was a different Shareshian and Wachs conjecture. So this
Sure,
is, yeah,
okay.
this is the other one.
This is E positive. Which now that we're working with like a Q analog, E positive means when you expand it in the E basis, all of your coefficients are polynomials in the Q, and those have positive coefficients. It's time I have. We're not going to get very far today.
Wait, why doesn't that imply the other conjecture then?
So this conjecture is stronger than the other one.
Oh, okay.
Yes. But in some way, these objects, just breaking them up into these quasi-symmetric functions makes them a little bit easier to work with. And so when Shareshian and Wachs reimagined the original conjecture using the quasi-symmetric functions, that sort of allowed a lot of progress, a lot of new families of graphs that they proved that this was true for. I'm going to say the name melting lollipop graph because I think it's funny, but I haven't read that paper yet. Okay. We're halfway through merging chromatic symmetric functions and Hessenberg varieties. Just reset this half of the board. All right, so where do varieties come in? This is an algebraic geometry seminar after all. So going back to a Hessenberg vector,
What was first between chromatic function and Hessenberg?
I think the Stanley Stembridge conjecture came first, and then in 2008, Juliana Tomasco connected them to the Hessenberg varieties.
Oh, I see.
Yeah. So given a Hessenberg vector, we're going to say the Hessenberg variety and, sorry, we also need a linear map from Cn to itself. I do understand capital X is being used for two different things, but it's going to go away soon enough. The Hessenberg variety is Hess of Hx is the set of all flags such that they're complete flags, meaning the dimension of the ith component is I, and the Hessenberg vector tells you something about containment when you apply the linear map. So I believe it is x of fi must be contained in F of HI. And this is, well defined because we have that weakly increasing condition, and every H sub I has to be at least I, and so this makes sense. And I think it shouldn't, I don't think it ever is empty, is it?
I think so.
Like it might be if,
Unless the linear map is something really weird.
yeah. Anyway, some examples. So when H is the all ends vector, this condition becomes null because X of Fi is always going to be contained in Cn, which is H sub I. This is the full flag variety. When H is 1, 2 through n, this is called the Springer fiber of X. I've been led to believe that this is a really cool thing that I know very little about. I think it's called Bx sometimes. Right, so this is the set of flags where for a given matrix, that matrix sends the I component of the flag to itself, right? Because that's what this Hessenberg vector is saying. When I apply X to F2, that has to be a subset of F2, because H of I is equal to I for all I.
Yeah, so a lot of times like X is like a nilpotent matrix or something.
Sure.
And that's when it's interesting.
Cool. This is a fact. When S is a regular semi-simple matrix, this is a smooth variety. So now I'm going to start using S for the name of my linear map.
In fact, doesn't that give an example of the thing being empty? So if X is full rank and not the identity, isn't that empty then?
When X is what?
If the map big X is an isomorphism but not the identity, and H is 1 to n, isn't then that's Hx empty, or am I?
Wait, so what was it?
If X is full rank but is not the identity, and in the second case where H is 1 to n, isn't that case the Hessenberg variety empty?
So usually X is nilpotent.
Yep.
In fact, I think it's usually defined, like Hessenberg varieties are often just defined for nilpotent X, right?
Yeah,
And
so
some-
there are nilpotent Hessenberg varieties. We're going to be talking about regular semi-simple Hessenberg varieties. Yeah. I think you're probably right.
But regular semi-simple could include the nilpotent X, no?
Yeah, probably.
Maybe I don't remember the definition of regular semi-simple.
Oh, well, I'm not going to tell you.
Okay, great.
So if a matrix is regular semi-simple, so regular means that the eigenvalues, if you put it in Jordan normal form, the eigenvalues for each block are distinct from each other. And semi-simple means diagonalizable because we're working over a finite vector space. And so S is going to be similar to a matrix lambda 1, lambda 2, lambda 3, lambda n for lambda I distinct from each other.
That's right, so this is like the opposite of the case you can do this regular varieties.
A little bit.
Yeah, you just get a different thing.
Yes. Okay.
What does the regular mean?
Regular means that when you put your matrix S into Jordan form, you get a bunch of, it's a block diagonal matrix with a bunch of blocks corresponding to the different eigenvalues. The eigenvalues for each block are distinct, so you don't get two different blocks with the same eigenvalue.
So all eigenvalues are distinct?
So because it is regular and semi-simple, yes, but not in general. If you just have a regular matrix, your Jordan form might look like lambda 1, lambda 1, 1, so that's a block. And then, lambda 2, lambda 2, 1, 1, 0, that's another block. So this does not have distinct eigenvalues, but the Jordan blocks are distinct from each other. But they have distinct eigenvalues.
Distinct, two Jordan blocks distinct eigenvalue, that's regular.
Yeah,
Okay.
I did. All right, so when we have a smooth variety, we like taking cohomology rings. So first of all, but we build up the cohomology ring of a regular semi-simple Hessenberg variety from the equivariant cohomology ring, which again is a long conversation that I don't have time for right now. The equivariant cohomology of Hessenberg HS is H star T So there are lots of ways, at least two, that I've seen of this being interpreted. One of them is the set of F, which is a vector indexed by elements of Sn. This lives inside of a large direct sum of polynomial rings. So we get one polynomial for each element of Sn, such that some stuff involving the Hessenberg vector. I'll write it down. So if I less than j is an inversion of W inverse, we need, and W inverse of I is less than or equal to H of W inverse of J. Then we're going to have some division relations amongst the entries of the tuple. So in particular, Ti minus Tj divides the function corresponding to W and the function corresponding to the transpose Ij times W. So it is this, subspace of a direct sum of polynomial spaces. This is kind of unwieldy to work around and talk through, but it can be visualized nicely in these things called GKM graphs. So GKM graph is another graph completely unrelated to the unit inflow graphs, where your vertex sets are elements of the symmetric group, and you get an edge whenever your permutations differ by one of these simple transpositions.
What is V?
This is the set of vertices of the graph.
What did you write?
This is Sn, sorry. So you get an edge whenever your permutations differ by a simple transposition, and we get something related to this. And for all I less than j, it's the same criteria in the inverse, W inverse. W inverse of I is less than or equal to H of W inverse of J. And we're going to label the edge by Ti minus Tj. Okay, again, this is annoying to work with. Let's look at an example. All right, I'm not going to draw a graph of 24 vertices, so we're going to ditch our 2, 4, 4, 4 example and look at 2, 3, 3. So this is corresponding to n equals 3, so our vertex set is the symmetric group on 3 elements, so there's 6 things. Let's not do this wrong. And we're also going to direct this sort of going down towards the simplest element. Okay, so here's the vertices. Here are some edges of the graph. Notice that we don't get this edge right here, even though these differ by the transposition 1, 3, because under this, so I would have an edge from here to here. W inverse of this is itself. This is its own inverse. It's a degree 2 permutation. So W inverse of 1 is 3.
What is W?
W is the permutation 3 to 1 in list
Oh,
notation.
okay.
Yeah. So W inverse of 1 is 3. W inverse of 3 is 1. H of W inverse of 3 is H of 1, which is 2.
Can I ask,
Yep.
in the definition, edge between what?
So we have an edge between W and the transposition IJ applied to W.
So
an
W
edge
and
between
I.
these two
Okay,
permutations.
okay.
Yeah. So maybe an edge W to V, if V is IJ times W.
I see.
Let's say that. So the reason we don't have this edge right here is because of the Hessenberg vector we have. If we look at W inverse of 1, that's equal to 3. W inverse of 3 is 1. We apply H to the latter and see that it's 2. 2 is not at least as big as 3, and so we don't have this edge. Whereas if we do this for like 1, 2, that would work out, and if we do it for 2, 3, that would work out. Right, and so there's a bunch of edges that are kind of missing that you otherwise might have. In addition, we label the edges by this polynomial corresponding to what transposition they differ by. So this edge is T1 minus T3. This edge is T1 minus T2. This edge is T2 minus T3. And so on. You can label all the edges in that way. And that gives you a nice way of visualizing this equivariant cohomology ring, because this is corresponding to a polynomial for each permutation in Sn. And so I can put a polynomial on each of the vertices. And then this division criteria just says if I have a polynomial here and a polynomial here, the edge label has to divide the difference. So as a little example, something like function 0, T3 minus T2, T1 minus T2, 0, 0, 0. The difference of these is T3 minus T1, which T1 minus T3 divides. So this lives inside of this equivariant cohomology.
What's S in your example?
S is a regular semi-simple matrix.
So whatever it is, it's
Yeah.
just.
It doesn't matter. I think, yeah, so this tells you that the cohomology rings are going to be isomorphic regardless of your choice of S, so long as it is regular semi-simple. Okay, and it's actually,
Any description for a Hessenberg variety in this case? Like what it is or something like that? Okay.
well, so it's a subvariety of the flag variety, but then it's going to really depend on what your H and S are.
So yeah, in this case, H is
Oh.
2, 3, 3, and one.
Yeah, so S, or S of 2, 3, 3,
Some S.
S. So it's going to be flags such that S applied to F1 is contained in F2, and the other criteria are automatically fulfilled. So this is really the only relation. So it's any flag, or when you apply your matrix to F1, it's a subset of F2. So you don't like go too far from where you.
I'm just curious. That's just
Yeah. Again, you can describe it more explicitly, but you would need a matrix. Okay, so this is the equivariant cohomology ring. And the normal cohomology ring comes almost for free. So the cohomology ring is the quotient of the equivariant ring by the thing. So I don't know a ton about equivariant cohomology, but I believe it has something to do with the things invariant under a torus action. And so the things that are invariant are polynomials where you just put the same element on every vertex or every node. So we're going to call that T1 vector, T2 vector, up through Tn vector, where Ti is the graph where I put Ti on every edge. All right, so you're looking at the set of those things, but anytime you have like a common factor of Ti, you can mod out by it. That gives you one way of visualizing the cohomology ring here. All right, I'll probably have to end with my next statement, given the time. But, well, I need two statements. Okay, so this is, you know, some funky polynomial ring. In particular, a polynomial ring in variables T1 through Tn, and so we can act on it by Sn. And we like group actions. I like group actions. I'm not going to say you like group actions, but yeah. So this is due to Moscow in 2008. And it's called the dot action of Sn on the cohomology ring. And I believe, but don't quote me on it, that she was the one that visualized this as GKM graphs. Yeah. Is if you have a so you have, let's let sigma be an element of Sn, and Fw, you know, some tuple living inside of this polynomial ring. Sigma applied to the tuple of Fw over W and Sn is, I always forget what this is. Where you go? There it is. So sigma, the permutation applied to just the list of indices, because it's a list of length. Why is it the list of length n factorial? It's kind of confusing. F sigma inverse W. So basically you take the inverse permutation and apply it to W, and then you apply the permutation sigma to what you get. So over here, let's apply something to this graph. Maybe, let me think about what a good one would be. There's options. That edge is, where's the graph? Okay, let's do 1, 3, because I know where that's going to go. So these vertical edges were labeled T1 minus T3, which means they corresponded to this transposition. And so the first thing is you apply the inverse of this to the indices of the polynomials. And so we're going to get T1 minus T2 and T3 minus T2. That's step 1. And step 2, when we apply the permutation, we flip across the edges corresponding to that. So we're going to flip across this axis, because these edges are the ones that correspond to this permutation. And so you flip it upside down, and actually you get back where you started. So this guy is fixed by this permutation. Kind of interesting. And the thing that ties together the Hessenberg varieties and the cohomology therein, and the chromatic symmetric functions, is there is a Frobenius map, which takes representations of Sn. Right, so this, this dot action can be represented as, a representation of the group Sn. So this is a theorem originally proved by, I always get the order wrong, who proved it first. It's been proved separately 2 times. So first by Brosnan and Chow. In 2015, and also by Guay-Paquet in 16. So I believe the first group proved it geometrically, the second group proved it combinatorially. Says that the graded Frobenius image of this representation, let's just say the dot action, is the symmetric function involution omega applied to the chromatic quasi-symmetric function. And so, understanding what's happening with this, action on the cohomology ring of the Hessenberg variety can give you insight to what's happening over in symmetric function land. And in fact, now that we have this group action, people understanding the representation has proved more things about the Stanley Stembridge conjecture and the generalized version by Shareshian and Wachs. And so this is what I'm currently working on. So for a very specific Hessenberg vector, h equals h1 n through n. Let me get their names right. Abe, Horiguchi, and Masuda found another way of sort of describing the cohomology ring that's not involving these GKM graphs. They gave generators, so it's a quotient ring of a polynomial ring. So they gave generators for the ideal. They gave a basis for the space. And they said, okay, now that we have these basis elements, we can look at the representation. And so what I've been working on is finding a little bit of a better basis so that the representation of Sn sort of falls out more nicely. I think that's my time, so thank you. Any questions? Yeah.
Just one small comment. This theorem by Brosnan and Chow and Guay-Paquet, this was the Shareshian Wachs conjecture.
Yes.
The other one is just like generalized Stanley.
Yeah.
So this one is the one that was called
Yeah.
the Shareshian Wachs conjecture, just to clarify the conjecture names and whatever. So yeah. But and this automatically gives sure positivity, if not positivity.
Yeah, so I think they proved her positivity a little bit before this, but this was another way of proving it. No? Okay. Then they proved her positivity using this.
This is how you make it prove sure positivity.